Okay, so hi everyone, Senan this side, and in this video we are going to solve shortest path in binary matrix. So what you would be given is an n cross n binary matrix named as grid. You have to return the length of the shortest clear path in the matrix. If there is no clear path, return -1. So what you have to do is travel through the nodes 0. So basically this is a graph problem, right? So you are going to travel through zeros and you can go to 8 directionally connected components. So you can go to right, bottom, left, up, basically north, south, east, west, and northeast, west, maybe all the 8 directions. Now if I go from here to here, what is the clear length of clear path? It's 2. Basically the number of locations that we visited is our solution. Now if you see, in this case it would be from here to here, then not here but directly here, then at the bottom. So we had 4 nodes in the path, so we return the output as 4. Now since you see the shortest path, right, the first logic would be to use something like Dijkstra's algorithm, that is for finding the shortest path from source to basically any node. But what we could do is, since we know that going from one node to the other node has a cost of 1, so that could be treated as the edge weight, and in this case the edge weight would be 1 for all the cases, right? Because we can only travel to at least one neighboring node in all the directions, so that would lead to an edge weight of 1. So in that case we could use something as normal, the breadth first search approach, and we can use to keep track the level that we are at. So basically the logic would be, let's say in this grid, first I push 0, then I in the queue, and then I find all the elements, all the neighbors in the possible 8 directions which have a 0 and which are not visited. If that is the case, I would push that into the queue. Now I am on this position. Now what I would do is I would find all the neighboring nodes which are in possible 8 directions. I would push that into the queue and increase the value of depth by 1. So at this point I am at a depth 1. At this point I am at depth 2. When I push these two nodes into the queue, I can reach these two nodes at a depth 2, 3, right? Basically I can go from this to this to this directly, or from this to this and to this directly. So these two nodes are at depth 3. Now when I try to do the next iteration, I push this into the this 0, the last 0 of this matrix, and this would be at a depth, what, it would be at a depth 4. Why? Because this is the closest one. So when you go through the breadth first search and you know that the edge weights are 1, so whenever you encounter a node, a new, for the very first time, you are visiting that node for the very first time, and the depth you have is the shortest depth because the edge weights are exactly 1. So that is the reason why you can use normal BFS and you don't need Dijkstra's algorithm. So the logic would be something like going through a breadth first approach. First of all, I get the size of this matrix n cross n. I create a visited array, and I create a queue of pair of ints. So basically keeping track of which node is in my queue. So row and column, we need two numbers to denote a node in this matrix. Now what I want is a clear path from the starting node 0, 0 to n minus 1, n minus 1. So that means these both nodes should be 0. Both the value at these grid should be 0, and if not, we cannot have a path, right? Path does not even exist. So that is what I do. If for some reason, if either grid of 0, 0 is 1 or grid of n minus 1, n minus 1 is 1, then we just return -1. We don't do any compute, right? Now what I do is I push the starting node into the queue and I mark that as visited, and I say that the current depth is 1. Now what I do is, if I get the size, if I get all the elements in the queue currently, and I take out the topmost element, get the node, and I pop that from the queue, and I check that if have I reached the final node. If yes, I just return whatever the depth is right now. Otherwise I would, for the elements in the queue, I would get all the neighboring nodes which are 0, which are not yet visited. I would take that into my queue. So I get this new row. So this is my way of going 8-way directionally, and I calculate the new row and new column. And if the new row and new column are within the matrix and it's not visited and the grid is 0, that means I can take that as a part of my answer, and the visited I can mark that as. And after I do this, I increase the depth because initially I have only a single node. Now I take that single node out in the first for loop. Now what would happen is the neighboring nodes of this node would be in the queue which are at depth 1. Similarly, I would, for the in the next iteration I would go through all the elements at depth 1, find all the neighbors that are not visited and marked as 0 in the grid. I would call them as at depth 2. So basically what you could do is possibly you could have a triplet. You can store either a vector or a pair, right? So pair of int comma pair of pair of int comma int. So basically in a way you can get the triplet denoting the nodes, the particular location of the nodes, row and column, and the distance that is required to reach that node. So you can do that, but since the edge weight is exactly 1, I can initialize the depth counter and I do this. And in the end, if I am not able to reach at any point, I'm not able to reach, I would return this as -1, because let's say for example, this was also 1, or let's say these two elements are 1, this is 0, this is 0, this is 0, but these two elements are 1. So I go here, then I go here, then seeing all of these as 1, I cannot push any more elements into my queue. So my queue would eventually have no elements. So in that case, I would never reach depth n -1 comma n -1. And yep, in that case, I just return -1 denoting that there is. So if you see very well, and this is also fine. Now what is the time and space comp? So it's exactly what it is of the preco search, and in this case it would be order of n squared for both time and space complex. Obviously you can calculate the exact amount of exact coefficient, a rough coefficient, because for every, in the worst case you would put all the elements into the queue, and for every element you would check 8 neighboring nodes, basically 9, but that would not be included because you mark that as visited, right? Initially you marked it as visited, so when you go to n row and n column, that would already be marked as visited. So in that case you would basically check 8 directions, technically 9, but you would actually be really checking the 8 possible nodes, so 8 times n squared, something like that. So the time complexity and spacity would be order of n. So yep, that was the video all about. You can also not use this visited array. You can do this in place using the grid matrix, because you can mark that grid as a value, let's say 2, and you consider that. And why is that the case? Because you know that the value of grid I or j, grid I of j, I and j is either 0 or 1. So if you see a value other than this, that means you had visited that element some point of time in some point of time back. So uh, you can actually somehow omit this, and in the end, if you want, you can restore the grid by saying that all the elements in the grid that are 2, make that to a 0, and in the end you would have the solution in place and you would return the grid as it is. So yep, thanks for watching, and I'll see you in the next video.